Hi there folks, this is just a quick video doing basically a walkthrough of one of the foundation mocks to help you prepare for next week. So what we're going to do is just sort of have a look over each question and just sort of see how we'd approach it and what it's about. Now what I will do with this video, as you can probably tell, my phone is balanced on top of a box. I might have to move it back and forth a few times, but I'll try and make it so you can always see the question. The webcam clip isn't working for some reason, it won't turn on. Right, so this is the foundation paper. So this is the one that I handed out in lesson. So you can see here it's the specimen 2018 paper with an hour and 15 minutes. So let's get stuck in, let's crack on, and let's see what this is all about. So you can see this first question, it's definitely a paper one question. This is about the pH scale, which is obviously all to do with the acids and bases topic. Okay, and I'm just going to sort of jot in what topic each question is on. I think it's quite a nice easy question. So it says draw one line from each solution to the pH value of the solution. Well, all this is testing is that you know what the pH of an acid will be, and it should be below 7. So there's only one answer that's right there. It must be 5. And then neutral, again, that's testing that you know that neutral is pH 7. So that's a really easy 2-mark question to get us started. And then below here is another related question. It says which ion causes acidity? Well, if you look at these here, there's two main suspects, which are H plus and OH minus. OH minus is to do with bases, this is to do with acids. So we'd of course tick that one. You'll notice it says tick one box. So if you tick more than one, you have to very clearly cross out the one that you changed. Okay, and I've already got myself 3 marks. So let's keep on going. Now on this side, it talks, this is more about sort of general chemistry knowledge. You can see it's multiple choice again. So it asks how many elements, not atoms, how many elements are in the formula H2SO4. So the trick on this question is that you know what an element is, and obviously an element is each one of the letter types. So clearly there are only 3 elements in H2SO4, although there are a total of 7 atoms. So 7 is almost a trick question on that one. And what type of reaction is this? Well, if you look, you can see we've got an acid reacting with a base. It says there's sulfuric acid added to sodium hydroxide, and that is always a neutralization reaction. Neutralization reactions are where we react an acid with a base. And then we've got our first sort of not multiple choice question. So it says name the salt produced. Well, we're adding sulfuric acid. You don't have to write this in on your answer, but I'm just doing this so it's easier for the video, to sodium hydroxide. And all that you ever do is you look at the acid that you're using. Okay, so this is sulfuric, and you look at the metal in the base, and the metal goes first, so it's going to be sodium, and then sulfuric acids make sulfates, and you can either write it with an F or with the traditional pH, if you will, and that will be the answer there. The answer is sodium sulfate. Okay, so I'll be putting the mark scheme up alongside this, and you can sort of check over that for yourself, but that broadly agrees with what we've said. So tot up my marks, and we've got the last bit of this question, I think. So this is the first longer written question you've got, and it's a 3-mark question. It says describe how an indicator can be used to show when all the sodium hydroxide has reacted with sulfuric acid. So this is, bits of this are difficult. You're going to get your first mark for just saying to add your indicator to the sodium hydroxide solution. You could also add it technically to the sulfuric acid. It doesn't matter. The first mark is for saying that you're going to add your indicator to it. Okay. Then what you would do, obviously, if we want to sort of show when it's all been reacted with it, we're going to add our acid slowly or gradually until the indicator changes colour. Or you could say, it's a bit of a weird one, until the universal indicator, that's UI there, goes green. It's a bit of a weird question, that one, because it's asking you to sort of think about how neutralization would go. So the first mark is for saying, obviously you just need to add an indicator to the thing that you're looking at. Then you add your acid, if it's a base that you've put in the first bit, or flip it round, it'd be a base and an acid. And then once the indicator's changed colour, that tells you, you know, when you've got a neutral solution, so it's all reacted. But again, on that one, even if you don't get all the marks, 1 mark there just for saying add an indicator, that's not bad at all. So obviously we're done with question 1 there. That was out of a total of 9. So obviously I'm on 9 out of 9 so far. Let's keep on going. Right, so we've then got question 2, and this is about John Newlands, who briefly talked about at the start of the year. You don't really need to know anything about Newlands, but he was involved in some early periodic table designs. And what he's asking you to do here is identify the names of the elements in group 5. I think this is really easy. It's carbon and silicon. And obviously you could use your periodic table if you weren't sure to look up those symbols. This one here, in what order is the modern periodic table arranged? So this is where, again, you can actually dig out your periodic table and use it to help you if you wish. What you'll notice is that things are arranged in order of their atomic number. Hydrogen starts off at 1, helium is 2, lithium is 3. Their atomic number goes up 1 each time. So it is the atomic number that it's arranged in order of. And then this here really is, again, you'd want your periodic table in front of you. I've not got one here. They've got one hanging on my wall, but I don't really want to rip it off. So it says, give 2 differences between group 1 of Newland's table and group 1 of the periodic table. So obviously I need to look at group 1 in the Newland's table. And I can see it's got hydrogen, fluorine and chlorine in it. Well, if you look at group 1 on the periodic table, okay, the first difference would be group 1 on the periodic table does not contain those elements. It doesn't have the hydrogen, fluorine and the chlorine. Okay, arguably you could say hydrogen's part of group 1, but it's not really. And then the other thing that we could say is that on a proper periodic table, hydrogen, fluorine and chlorine are not all in the same group. Okay, so if you look at on a periodic table, fluorine and chlorine are in group 7, but hydrogen is just sort of on its own at the top. You could say, instead of this bit at the top, I'm not going to write it out, but you could have said the opposite. So you could say group 1 on the periodic table does contain lithium, sodium and potassium. That would also get you the mark. So it's 1 mark for saying either the group doesn't contain these elements or it's got other elements in that aren't those ones and you've listed them. And then the other one, which I think is probably a bit of a tricky mark, is for saying that the hydrogen, fluorine and chlorine on the proper periodic table aren't all in the same group. Okay, so tot up our marks there. Move on to the next bit of question 2, and we've got our first fairly lengthy question. Okay, and this is all about models of the atom, which we covered right back at the start of the year. So let's read the question carefully. It says, in 1864, atoms were thought to be particles that could not be divided up into smaller particles. By 1898, the electron had been discovered and the plum pudding model of an atom was proposed. So here in figure 2, we've been shown the plum pudding model, which is here, and we've also got the nuclear model, which is the model that we sort of currently use at GCSE. So it says, compare the position of the subatomic particles in the plum pudding model with the nuclear model. Well, the subatomic particles, this is talking about our electrons, protons, and neutrons. Okay, and that is what we're going to need to talk about in our answer. So I think the first thing should be quite obvious if you look at it, okay, is that the plum pudding model has basically just got a positive charge is this sort of single ball here. It's this ball around here. So that would be my first kind of comparison to make, is that the plum pudding model I suppose you could say has no protons or, neutrons labelled, and shows the positive charge as a ball, okay, that covers the whole, area of the atom. Okay, and also we can look here, the plum pudding model just sort of has the electrons in random locations. Okay, so the plum pudding model has no protons or neutrons and shows the positive charge as a ball. The plum pudding model has the electrons in random positions. Okay, so what we can do is we can sort of link this now to how it is in the nuclear model. So in the nuclear model, the electrons are fixed. Okay, and what we can say in this one, in the nuclear model, they are found in the nucleus. And those, it's quite a hard question, this one, I must admit, for a fairly early on in a foundation paper. But the next bit is quite easy. So we basically said now, where are the positive charges and the negative charges? So we've dealt with electrons, protons, and really we've dealt with neutrons as well. But we've got to talk about the nucleus, okay? So this would be the other thing to say. The plum pudding model has no nucleus. Okay, and what we could also say is that the plum pudding model has no neutrons. Okay, so by doing that, you've talked about all the subatomic particles, the electrons, the protons, and the neutrons. And that is quite a common question, I must admit, where they'll get you to compare one atomic model with another one. So hopefully that was somewhat useful for you. And as you can see, even if you don't get all 4 of the marks, chances are you're still going to pick up some by mentioning some of the obvious stuff, like one's not got a nucleus and one does. One's got fixed, not got fixed electrons, one does. This has got a ball of positive charge everywhere, this one doesn't. Even if you didn't know much about chemistry, you can see that these two things are different. Okay, so got 4 there. Moving on. Nice easy question here. So we've just got basically what looks like a load of balloons, okay, a load of models, and it says which one shows a model of a mixture. Well, as you know, a mixture contains a mixture of different either compounds, elements, whatever it might be. Well, these are all argon, these are all nitrogen molecules, and these are all carbon dioxide, which is a compound, but every single thing in there is CO2. So that's pure, that's pure, that's pure. This is the only one we could say is a mixture. Okay, moving on. So we then got 2.6, which is a quite easy question. So it says, what does each line between the atoms in figure 3 represent? Well, if you look at it, this is a this is a non-metal, that's a non-metal. So clearly it's covalent bonded. It wouldn't be an intermolecular force because that wouldn't, you don't draw those like bonds. And it can't be ionic or metallic because that would need to be between a metal and a non-metal, or a metal and a metal. Okay, so not too bad there. Next question, bit tricky. So this is a bit of a long and detailed one. So it says, number 3, some students investigated the reactivity of 4 unknown metals, W, X, Y, and Z. And the letters, just FYI, are not the symbols of the elements. Okay, there is an element with the symbol W, which is tungsten. Don't get it mixed up. So what they said, they've used solutions of copper nitrate, magnesium sulfate and zinc chloride, and they've given an overview of their method underneath. So it says they're going to pour a solution of metal salt into a glass beaker. They're going to measure the temperature of the solution. They're then going to add a gram of metal to the solution, measure the temperature, and calculate the increase. So what this should get you thinking is that this is about endo and exo. And for some reason, sorry, I forgot to put the topic on the last question. So for question 2, it was a bit of a mixed bag. But this was all about basically the periodic table and a bit about, elements and compounds. So, question 3, endo-exo. We've seen the setup. What are we being asked to do? Well, it says here we've got some results, and you can see from the results we've got 3 different solutions and then our 4 different metals, metal W, X, Y, and Z. And it asks you which one is the least reactive. Now, this is very easy to get confused about, and you might look at the things in this table and the numbers and think, well, this one's giving me a temperature change, this one's giving me a bit of a temperature. You might stress over that, but the simple reality is only one metal has reacted and had a temperature change with 2 things, and that's metal W. Metal X hasn't reacted with 2 of them. Metal Y hasn't reacted with 2. Metal Z hasn't reacted with any of them. So clearly that can't be the most reactive. These 2 are, well, that's slightly more reactive than that one because there's a bigger temperature change. But this is the only one that reacts with 2 substances. Okay, so in this case, the least reactive one, the one that does the least reacting, is metal Z. Sorry, I was thinking most reactive for a minute. So how do the results show that magnesium is more reactive than metals W, X, Y, and Z? So if we go back to the bit, I think it's on this side. I don't quite know why they're mentioning magnesium. I'm not sure if that's a typo. That is a bit strange, that. So effectively, what I think they're getting at here, because they've not said what magnesium is anywhere. I've just realised that. It literally does not mention magnesium in this question, apart from here, where they say magnesium sulfate. Strange. Anyway, we can still answer the question. So what we can say, or is it magnesium sulfate? I think they mean magnesium sulfate. Right. So apologies about that, folks. That's obviously the exam paper's fault. So the magnesium sulfate is more reactive than these metals. Well, the way that you can tell is that it didn't react with any of them. Okay, you can see there, no change for the magnesium sulfate, and that's because it does not react with any of the metals. And as you know, if you're more reactive than something, then that doesn't necessarily mean that you're going to react. You're not going to have a temperature change. So moving on, question 3, this is easy. How do the results show that the reaction between metal Y and copper nitrate solution is exothermic? Well, there's our copper nitrate, there's metal Y. We can see the temperature has gone up. Okay, and that's literally it. We just say the temperature has increased. Okay, so question 3.4 now. It says, one student said the investigation was not valid, i.e. a fair test. Write a plan for the investigation that includes some improvements to the method and apparatus. And I would say that, yeah, it's not a particularly great method. So if we look back at it, you can see here they've said pour a solution of metal salt into the beaker, measure the temperature, add a gram, measure it, and then calculate it. Okay, at no point have they put any insulation on this beaker. At no point have they repeated their results or put a lid on top of the beaker. They could have a set amount of time that they're going to leave it for, because they've not talked about the amount of time that they're going to do it. They've just said they're going to add it and measure the temperature of the solution. Maybe they could measure the highest temperature that it reaches. Okay, maybe they could repeat their results many, many times. So I'm just going to write a sort of simple plan for the investigation that includes improvements. I'll try and do this fairly quickly. So I would say pour a fixed volume of metal salt solution into an insulated cup. And obviously I'm writing a plan, so that means that I do have to, it has to be like a set of instructions I can follow. So record the temperature of the solution, add 1 gram of metal and stir, and then I'd probably put a lid on and record the highest temperature reached, because that would be a lot better than just randomly recording the temperature. It wasn't very specific about that in the last one. And then I would say that, doing an experiment one time, not particularly great. Yeah, you can see there we've just done each metal with each one once. So I would say repeat each experiment at least 2 more times and calculate an average. And that's always a good thing. If you're asked to improve a method, that is always a good go-to statement, that one down there, about just, you've got to say at least 2 more times. If you want to calculate an average, really you need 3, I can't work out where my hand is realistic, you need 3 different results, okay? So hard question again there. That one, it does sort of cut across both papers on the higher end foundation, that one for this year. So still on question 3, and then we'll be moving on. This next bit's nice and easy though. So it shows you the reaction profile for an exothermic reaction, and it says what is the energy value of 1370, this bit going up here representing, well, as you can see, this is the little hump that we've got to get over to get from reactants to products. So that means that is the activation energy. It's what we need to start the reaction. Then underneath here, this one, I remember a few people were asking me in lesson about this one. So doing a percentage. So percentages is something you can be asked to do on GCSE quite a bit. And all that you need to do really, say for this question, it says the overall energy change is 386. What percentage of 1370 is 386? So all that you do, if you're asked to take a percentage of something, so what percentage of 1370 is this? Well, 1370 is going to go at the bottom, okay? And you're going to divide the number here by that number, and then you're going to times it by 100. Now in this case, that's going to give you 28%, okay? But there was something I was showing in lesson. Let's say you got this wrong and you did 1370 over 386, and then you times it by 100. Well, you're going to wind up, just dig me, oh, my calculator's on my phone, so we'll just do this on the computer. So if you do that, then what you'll find is that you get an answer that is bigger than 100. Okay, and if your answer is obviously bigger than 100, it's not going to be a percentage as we understand it. So, oh, it doesn't seem to have a calculator at all. Let me just search. Right, so there we go. Let's just use the one on the internet. This computer's not having it. So if I do 1370 divided by 386. And times it by 100, I get 355%, okay, which is clearly not right, is it? Okay, so you do that and you go, no, that's not right, I need to swap them over. Okay, and that's always a common thing that a lot of students do. Always remember to write your answer in the answer box though, just in case. Okay, so then there's sometimes you get pages like this, there's just paper for paper's sake, just turn over. Okay. Question 4 now. So this is a bit of a weird one. So this has got a bit on melting points. And then it talks about, yeah, I'd say this is really about purity and melting points. And changing states. So states of matter. Okay, so it says the 3 states of matter are solid, liquid and gas. Lithium reacts with water to produce lithium hydroxide solution and hydrogen. Use the correct symbols from the box, so we've got these 4 here, to complete the equation. Now if you look, you can see, obviously this one must be a solid, this one must be a liquid, and then we're just sort of told, work it out, what are you going to put as your answers? Well, I think one of these should be pretty obvious. Hydrogen is a gas, okay, so it's something you do need to know, that hydrogen naturally, like oxygen, is a gas. So that is a gas. The issue we've got here is that the lithium is dissolved in the water. And if something's dissolved in the water, we can't call it a liquid. We call it aqueous, AQ for aqueous. So that is an easy drop, easy mark to drop. But if you can work out that, when something's been dissolved in water, it must be aqueous, then that is going to be a good one to remember. So if you get 1 mark for each one of those you can get. And then we've got this quite strange thing here for figure 6. So for figure 6, it says it shows the melting points and boiling points of 4 different substances, A, B, C, D, and then there's E on here as well, which will be relevant, I'm sure, in a moment. So it says which substance is liquid over the greatest temperature range. So if we look at this, you can see here, this bit of a weird question. We've got this key. It says melting point and boiling point. So this is getting you to use your noggin a little bit. If something melts, what that means is it goes from a solid to a liquid. If something boils, it goes from a liquid to a solid. So if I'm looking at these lines, if this is the melting point, so in other words, where it goes from a solid to a liquid, obviously you don't need to do this on your graph, but below that bit there, it must be a solid because it's not melted yet. Beyond this bit here, it must be a gas because now it's boiled and it's become, why have I written liquid to solid there? Sorry. And it's become a gas, okay? So therefore here in the middle on these lines, it must be a liquid. So it's pretty obvious which one was a liquid for the biggest range, and that is C. So it says which two substances are gases at 50 degrees Celsius? Well, again, here it's getting you to think about what we've done there, okay, knowing what a gas would be. So here's my 50 degrees C, okay, and I could just do a little line across. Okay, so I can see this one here must be a gas at that point. This one hasn't yet melted. This one is a liquid, and that one is well and truly boiled by that point. So it would be A and D are your correct answers for that one. It can't be any of the others. It has to be those two. So it then says, this is a plotting question. A different substance E has a melting point of -50 and a boiling point of 120, and it wants you to plot those values. So we've got the melting point where we're doing a cross, and that needs to be at -50. And then we've got the boiling point at 120. And again, this is getting you to use scaling. So you can see 120 isn't written here on the side. So we need to think, well, it's going to be just below halfway between those numbers, because half of 50 is 25. So I would imagine it would be about there, or so. And that, obviously, each one of those gets you a mark. Okay, and it's the accuracy of the plot that determines how many marks you got for that one. But I think that's a bit of a weird question, but a useful one to have a look at as an example. Okay, carries on question 4 now, talking about this setup here. So we've got figure 7, shows the apparatus a student used to determine the melting point and the boiling point of substance B in figure 6. So this is basically how we got, the data that's there. So explain why the student could not use this apparatus to determine the boiling point of substance B. Let's have a quick drink. So this is bit of a weird one, but actually really logical when you think about it. So it says substance B, okay, and the big clue there is that we're probably going to need to look at this data that we've got on substance B. So if you look at this, you can see we're being asked to talk about the boiling point of substance B, and the boiling point is up here. Okay, you can see the boiling point for this looks like it's about, about 190 degrees Celsius or so. Okay, now the problem we've got, if you look at this setup here, we are boiling water, and as you may know, the boiling point of water is only 100 degrees Celsius. So this wouldn't work, because if we want to boil this substance, we need to get to a higher temperature than the water can actually reach. Okay, so what we would say in our answer is that water has a boiling point of 100 degrees Celsius, but substance B has a boiling point of 190, so it will not reach it, and therefore it will not boil. Okay, so the first mark there is talking about the boiling point of water, and the second mark is obviously saying that because that is the boiling point, we're never going to get our substance B hot enough. It then says, suggest one reason why the student could not use this apparatus to determine the exact melting point of substance B. So we go back and we look at the melting point of substance B. You can see it's around about 50 or so. Basically, the issue that you've got, and I think this is probably one of the hardest questions on the paper, if you want to melt something, say like a chocolate or whatever it might be, well, it's not all going to it's not all going to melt immediately. So it's not all going to melt at the same time. So the key word here is this bit about exact Okay, there's a couple of things you could say here, but what I would say is there is too much substance B to melt instantly, so we wouldn't be, it would happen over a range of temperatures. You could also say, I suppose, so actually it will take a while for all the heat to conduct to the thermometer. So, if you boil a liquid, then the liquid moves, okay? So the temperature in the liquid is generally uniform. Whereas if you're trying to measure the temperature of a solid, it might be the bit that you're dipping it in is quite hot, but the bit that's further away is a bit colder. So I genuinely think it's only a 1 mark question, but I think that's actually one of the hardest questions on the paper. So moving on to another blank page. Right, question 5 we're going to come back to in a minute, because this is a 6 mark question. And as you can see, it tells us about apparatus, and we've got to say how we're going to make a salt. So what we're going to do, we're going to pop back to that one in a minute once we've gone through the rest of the questions. Okay, just because I tend to do that myself, I tend to leave 6 marks to the last. Okay, moving on. So now we're on to, as you can probably work out, this is about electrolysis. So we've got electrolytic cell, and then I think, yeah, it's all about electrolysis. So this one, quite nice. So it says, what's the name of the process in figure 9? I've probably kind of given the game away on this one. It is electrolysis, but just remember what electrolysis is. It's using electricity to make elements from a solution of ionic compounds or from a liquid ionic compound. And the thing that gives it away is you'll always have 2 different electrodes dipped into some solution or into a liquid. Okay, so nice and easy there. Next bit, not quite as easy. So it says table 2 shows the products formed when from 3 experiments using different compounds in the apparatus shown in figure 9. So here's our compounds: copper chloride in molten and aqueous solution, and we've got potassium bromide in molten solution. And it says use table 2 to name the products formed at each electrode if using an aqueous solution of potassium bromide. So you'll notice that isn't one of the things in the table. You have to do a bit of thinking. So the first thing to think about here is you need to know your anode and your cathode. And remember, the trick is not to panic, okay? If you panic, you'll remember that the positive is the anode and the negative is the cathode, okay? So knowing that, clearly the thing that's positive is going to go to the cathode and the thing that's negative is going to go to the anode. So if we're doing potassium bromide, you can see that when we did copper chloride molten, we got copper and chlorine. When we do potassium bromide molten, we get potassium and bromine. But when we did copper chloride in aqueous solution, we got copper and chlorine. This time, we aren't going to get potassium and bromine again. And the reason for that, another tricky one here, is that potassium is a very reactive metal. And the rule with electrolytic solutions is, if it's really reactive in an aqueous solution, then it gets left behind. So what we would actually find at the cathode is we would form hydrogen, and at the anode is where we would get the bromine. In my opinion, again, one of the toughest questions on this paper is that one there. And I would suggest, obviously, reading over your electrolysis stuff if you find that difficult. So it says, explain why copper is formed at the cathode during the electrolysis of its salts. This is a bit easy, okay? So copper is a metal, okay? And that means that copper forms positive copper ions, okay? And what we can say is the copper ions are attracted to the negative charge or to the negative cathode. You could even go further into detail and say because they want to gain electrons, but I would say you're all good with those two there. Okay. Right, we're getting there now. Only a few more questions, then we'll go back and check that 6 marker. So this is question 7. So it says the question's about calcium. Now this is a question about bonding, really. So you can see we've got a nice bonding question there. So this is all about bonding. It says, what type of compound is calcium oxide? Now, we covered this in lesson. Calcium oxide, because it's made of a metal and an oxygen, right? It's a metal oxide. All metal oxides are bases. Okay, and again, that is another tricky, easy mark to drop there potentially. You need to say that it's a base. Any of the other options aren't appropriate here. And again, I think 7.2 is nice and easy. It says, calcium oxide has a giant ionic lattice in which there are strong electrostatic somethings of attraction in all directions. Well, clearly, it's going to be forces. Okay. If you're ever talking about electrostatic attraction, it's the forces of those attractions. And then 7.3 is a classic, and we looked at this a bit in lesson, is a classic ionic bonding question. So I won't spend loads of time on this. What you need to say, what loses electrons and how many, what gains electrons and how many, and what's the charges on the ions. So we can see here the calcium loses 2 electrons to become calcium 2 plus. The oxygen gains 2 electrons to become O2 minus. This results, or this transferal of electrons produces a strong electrostatic attraction. So I've gone over the top on this. Okay, you don't really need to chuck in that bit at the end about strong electrostatic attraction, but I'm just covering all of my bases. So here I've said calcium loses 2 electrons, oxygen gains 2 electrons. I said what ions they form. I just sort of covered me back here by saying that as a result of doing that, the ions are going to be attracted to each other. Don't forget to practice as well how to actually draw the dot and cross diagrams. Nearly there now, and then we'll go back and we'll check question 6, I think it was. So last question here, again, we sort of had a look at this in lesson, so I'll rock it through. So this first question here, obviously this is fairly early on the higher paper, but it's quite late on the foundation paper. So this is just a simple conservation of mass question, but the overall topic really is about, it's that metals and a bit of the calculation stuff. So it's metals, but it's mixed in with stuff from the calculations topic, which was topic 3. So all we've got to do here is simple conservation of mass. Okay, so the conservation of mass says that, you know, if you have so many grams at the start of a reaction, you must have the same amount at the end. They might have moved around between chemicals, but they'll still be there. So we can add this onto here. If I've got 1615 of this over here, and I make 1989 of this, and I react it with 782 kilograms of that, well, all we need to do is add up 1615 plus 782, so we can work out the total on the left. So I'll just do that on my computer. Where's my calculator gone? Okay, so just give me a moment. So yeah, 1615 plus 782. Oh, I need to turn my num lock off. Gives you 2397. And then all we need to do is take away the 1989 from 2397 to get the final answer, which is 408. Yes, 408. So 408 kilograms for that one. Definitely a question that a lot of people would just move on from that. But if you can remember to spot conservation of masses questions like that, then you know it's easy marks to pick up. Easy, but extra marks to pick up. So we looked at this one yesterday. Sorry, not yesterday, but when we were in lesson. So I'm not going to spend a lot of time on this. this is a graph plotting question. So you've got to plot the data onto the graph, okay, like so, and then it wants you to draw a line of best fit. The only thing I would sort of say is that you need to remember that your line of best fit needs to be a straight line that passes through, you know, kind of the majority of your points. Okay, getting there now. Last few questions. So question 8. So this is a bit of a weird one. Again, we had a talk about this in lesson, and I think it was Andy had done it in a slightly different way to how I would do it. So it says the product, sodium chloride, is dissolved in water to separate it from titanium. At 30 degrees Celsius, the solubility is 36 kilograms per decimeter cubed. So it's saying calculate the minimum volume of water at 30 degrees, so you needed to dissolve not 36 kilograms, but 1,989 kilograms. Now, there's a few different ways of doing this. I personally would do 1989 divided by 36, okay? Because that's going to tell me how many times 36 goes into 1989. So let's write that through on the computer. So 1989 divided by 36 equals 55.25. Okay, so in other words, so we've got this number here now. And then all I need to do is times that by 100, because obviously it's per 100 decimeters cubed. So if we want to get that in decimeters cubed as well, we times that by 100. That's going to give us the answer, which is 5525 decimeters cubed. Because if that was sort of kilograms, we need to times it by the 100 decimeters to work out the total number of decimeters. So the final answer will be 5525. That's our question. We then got a percentage by mass question. This is not too difficult in my opinion. So it says we need to work out the percentage of titanium in titanium chloride. So what we've got to do, you can see we've been given some RFMs here. That is a big clue that we need to add them all together to work out the total. So for TiCl4, that's going to be 48 plus 4 lots of 35.5, which is going to be equal to 190. And then all that we need to do, we need to work out what mass of titanium is in this 190. So just like the percentage question we did before, we take the smaller number, which is 48 for the titanium, and we divide it by 190, times it by 100. That's going to give you your final answer, which again, I'll just run through. Where's it gone? Question 8, is it? Yeah. So that gives, 25.3%. Okie doke, so we're nearly there. Last couple of written questions, then we'll go back and we'll check that 6 marker. So question 8.5 says suggest why the reaction is done in an atmosphere of dry argon instead of an atmosphere with water vapour. Well, again, if you look at what we're doing in the question, there's a lot of times you might need to do this, which is sort of flip back to the original question and check what you're talking about. So it says basically, why are we doing this in an atmosphere of dry argon instead of with one that's got water vapour in it? Well, if you look here, we've got sodium. One obvious thing is that sodium is very reactive. So what we could say here is that argon is very unreactive. Sodium would react with water vapour, and that could be dangerous. And also, the air could contain oxygen, which could react with the chemicals. And there's a few things you could say here. You could even say that the water vapour would react with the titanium chloride. The idea being, the main kind of mark there is saying that argon's unreactive. Sodium, therefore, if we've got argon in there, isn't going to be able to react with it, but it would react with water vapour, and the air contains the oxygen. And then question 8.6, this is just a metallic bonding question, okay? So it's asking, why does titanium conduct electricity? Well, that's because it's got essentially electrons in their outer shells are what we call delocalized. What that means is they're free to move throughout the structure. Which means they can conduct electricity. Okay, I don't know what's going on with my handwriting there. So, essentially that there is about the property of a metal. This one here is getting you to think about properties of really group 1 and group 7 actually. Bit of a weird question. So just be aware, your last question on any paper, whether it's foundation or high, doesn't matter, will always be a bit weird like this. So let's just go back and let's look at question 6. Now what I'd recommend you do is you have a look at the mark scheme when you're going through and you... sorry, not question 6, question 5. This was it, sorry. So the question was, we've got to, using this apparatus, outline a plan the student could use to make pure dry crystals of a soluble salt, like copper sulfate, from an insoluble metal oxide and a dilute acid. Now what I'm going to recommend you do here, because I could sit here and I could write out a lovely answer on the page, but this is a very common 6-mark question. It's writing a plan for making a salt. My recommendation would be that you get up the mark scheme and you have a look at question 5, okay? When you have a look, you'll see it's quite a long, lengthy thing, but one of the boxes, I think it's the bottom one, says indicative content. And basically, what you're looking for is you're looking at the method and the safety bit. You need to, in your answer, have somehow described what you're going to do. You need to say that you're going to take your metal oxide, which is copper oxide in this case, and you're going to add it to sulfuric acid. And that's actually your first kind of couple of marks, because they've not told you in the question what chemicals you can use. They've just said you're making copper sulfate. So you obviously need to think, well, I'm going to need something, I'm going to make copper sulfate, I'm going to need sulfuric acid and copper oxide. And that will be your first jumping in point. But then you're going to need to say what you're going to do with that. So I would recommend, if you can, have a look at the cognato on making salts. And have a good look at the mark scheme on that one. Because like I say, I could write a method, but it's more about you writing your method and being able to do that reliably for that one. So I hope that was useful. It's quite a lengthy video, but obviously we've got to go through a whole paper and cover all the stuff. So I think given it's an hour and 15 minutes paper, that's not bad. So I'll upload this onto the Teams. Yeah, hopefully you found that useful. Make sure you keep on cracking on and revising, and I'll catch you all soon, folks.